Black holes are some of the most mysterious objects in the universe. How are they born? What happens as they grow, and can black holes really die? In this video, we'll explore black holes from birth to death, explained simply. If you enjoy learning about space and science in an easy way, don't forget to like the video, subscribe to NOAA Science, and share it with someone who's curious about the universe. Thank you so much for watching. Let's begin. In a cold region of interstellar space, long before any black hole takes shape, a cloud of gas and dust hangs almost unchanged for millions of years. It is mostly hydrogen, the simplest atom spread so thin that an individual particle can travel for long distances without striking another. Gravity is weak in this quiet place, but it never truly switches off. Every atom attracts every other atom. Over time, imperceptibly, gravity begins to draw the cloud together. Denser knots form small at first, then larger, as nearby material drifts inward. The cloud, once diffused, develops clumps that slowly collapse. As each clump contracts, gravitational energy converts into heat. The gas warms. Collisions between atoms become more frequent and more violent. The center of the clump, now a growing protostar, brightens in wavelengths of light that human eyes cannot see, while the outer envelope remains cold and dark against the wider galaxy. This process of star formation takes place in many galaxies at many times. Telescopes operated by agencies such as NASA and ESA observe the cool gas with radio and infrared instruments tracing long dark filaments where gravity is quietly at work. The visible light images often show bright clusters of young stars surrounded by curving, shadowy clouds. But the essential physics remains simple: gravity pulls, matter inward, pressure pushes outward. And for a while, the two tendencies fight to a standstill. In the core of a forming star, density and temperature continue to climb. Hydrogen atoms are squeezed so close together that their electric repulsion can no longer keep them apart. Here, nuclear fusion begins. Two hydrogen nuclei combine to form helium, releasing energy in the process. This energy travels outward as high-energy photons and as the motion of particles. In effect, the star lights itself from within. The outward push from this energy balances the inward pull of gravity. The structure that results is called hydrostatic equilibrium. In this state, each layer of the star supports the weight of the layers above it. As long as nuclear fusion in the core supplies enough energy, the star maintains this balance. Its shape remains nearly spherical, its size almost constant, and its light output relatively steady. For a star with a mass similar to that of the Sun, this stable phase lasts for billions of years. Observers on distant worlds, if any exist around such a star, would see an ordinary yellow or white point in their sky, and might never suspect the delicate arrangement of forces that keeps it from collapsing. The same basic story holds for more massive stars, but with important differences that matter for the later birth of black holes. When a star forms with many times the mass of the Sun, its core reaches higher temperatures and pressures. Fusion proceeds more rapidly. These massive stars burn through their hydrogen fuel in a fraction of the time. They shine more brightly, often with a bluish or white color that indicates higher surface temperatures. Inside the core not only fuses hydrogen into helium, but as the supply of hydrogen dwindles, begins to fuse helium into heavier elements such as carbon and oxygen. In the most massive stars, this chain continues through a sequence of fusion stages, each requiring higher temperatures and each lasting for a shorter period. Although the details are complex, the guiding principle remains the same. Gravity tries to pull the star inward. Fusion in the core pushes outward by releasing energy. For a while, the two sides remain in balance. The star lives in a dynamic but controlled state, constantly adjusting to small changes in its interior. Slight increases in core temperature cause the star to expand and cool, which reduces the rate of fusion and restores balance. Slight decreases in temperature have the opposite effect, encouraging contraction and heating until the fusion rate rises again. This self-regulating behavior makes stars remarkably resilient. Yet this resilience is temporary. The fuel in the core is finite. Every photon that leaves the surface of the star represents energy that comes from fusion reactions deep inside, and those reactions steadily convert light elements into heavier ones. From a distant viewpoint, the star appears serene. Its surface may show storms and flares, but its overall brightness changes only slowly. Within the core, however, the composition is gradually shifting. The concentration of hydrogen falls. The abundance of helium and heavier elements rises. The balance between pressure and gravity depends on what is burning and how fast. In lower mass stars, the story can end without any black hole. They eventually exhaust their core fuel, shed their outer layers gently, and leave behind a dense white dwarf. In higher mass stars, the conditions move toward a more dramatic finale. Their cores become dominated by heavier elements more quickly. The energy gained from fusion declines relative to the gravitational pull of the overlying mass. At some point, for those most massive stars, the internal machine that has held gravity at bay will no longer keep up. The fragile balance that allowed them to shine will fail. An almost invisible threshold in mass separates stars that end quietly from stars that end in collapse. Two stars that look similar in a telescope can in fact be heading toward very different fates simply because one formed with slightly more material than the other. The cloud that once quietly contracted into a young star has now, over millions of years, evolved into an object poised on the edge of catastrophic collapse. The path from those first drifting hydrogen atoms to a future black hole is already set, even though the star still appears as a bright, stable point of light in the sky. The forces that sustain it are the same forces that will eventually undo it, and in that tension lies the seed of one of the strangest objects in the universe. In the late life of a very massive star, the quiet balance that once seemed secure begins to fail. The core has fused most of its hydrogen into helium, and over time, helium itself has become fuel. Under extreme temperatures and pressures, helium nuclei merge into carbon and oxygen. Later, in even shorter burning stages, carbon and oxygen fuse into heavier elements, such as neon magnesium silicon and others. Each stage requires a hotter core and proceeds more rapidly than the last. What once took millions of years now gives way to processes that unfold on timescales of thousands, then hundreds, then even fewer years. Above the core, the star still shines with fierce light, often blue-white, and drives strong stellar winds that peel away its outer layers. Telescopes that observe such stars in the Milky Way or in nearby galaxies see them as brilliant, unstable giants, sometimes surrounded by shells of gas expelled in earlier phases. Inside, however, the structure resembles an onion made of nuclear ash. Each inner layer supports the weight of everything above it. Each shell burns a different fuel with hydrogen still fusing in a thin layer far from the center, and progressively heavier elements burning in shells closer to the core. At the heart lies a region dominated by iron and nearby elements. Iron plays a special role in this story. Fusion reactions up to iron release energy. They convert mass into radiation and particle motion that help support the star against gravity. Fusion beyond iron, in contrast, does not provide a net energy gain under normal stellar conditions. When the core composition shifts so that iron becomes dominant, the star effectively reaches the end of its ability to power itself through fusion. In the dense core, iron nuclei are packed closely together. As the surrounding shells deposit more material inward, the total mass of the core climbs. The internal pressure increases, but the iron does not burn in a way that yields new energy. Instead, the core relies increasingly on quantum effects that allow electrons to resist further compression. This electron pressure can support a white dwarf, but in the heart of a very massive star, the mass of the iron core eventually exceeds the limit that such pressure can withstand. When that limit is reached, support fails suddenly. The collapse begins. In less than a second, the iron core falls inward. At first, it accelerates freely under gravity, and the outer layers of the star begin to follow. As the core shrinks, densities rise to values far beyond ordinary matter. Protons and electrons are forced together to form neutrons and neutrinos. Neutrinos stream outward, carrying away an immense amount of energy. The inner part of the core, now mostly neutrons, becomes stiff and nearly incompressible. When the infalling material slams into this newly formed neutron-rich region, it rebounds. A shock wave forms and tries to travel outward, pushing against the still collapsing outer core. Whether the shock succeeds in breaking through and unbinding the star depends on details that are still the subject of active research, including the behavior of nuclear matter, the role of neutrinos, and the star's rotation and magnetic field. In many cases, calculations and observations indicate that the shock does revive. It powers a supernova explosion. For a brief time, the dying star outshines its entire host galaxy. Observatories on Earth and in space have recorded such events, watching the light curve rise and fall over weeks and months. The expanding debris carries newly forged elements into space-seeding future generations of stars and planets with the heavy atoms needed for rocky worlds and complex chemistry. At the center, the collapsed core remains. If the mass of this remnant lies in a certain range, the result is a neutron star, an object only a small number of tens of kilometers across, but containing more mass than the Sun. If the remnant mass is higher, gravity overwhelms even neutron pressure. The core continues to collapse. No known force in standard physics can halt that inward rush. The boundary that forms around this region from which not even light can escape is the event horizon. The exact outcome depends sensitively on the mass and structure of the star at the moment of collapse and on the behavior of matter at densities that are difficult to study directly. Astronomers infer the formation of black holes from the absence of visible remnants and from the later appearance of compact invisible objects that reveal their presence through their influence on nearby matter. In some cases, massive stars may even collapse directly into black holes without a bright visible supernova, producing a much fainter display that is hard to detect at great distances. This diversity of endings suggests that stellar death is not a single simple process, but rather a family of related outcomes shaped by initial mass composition and environment. Behind all of them, however, stands the same basic pattern. Fusion builds heavier elements until iron dominates, support fails, and gravity takes control. In that final handover from pressure to gravity, a star that once illuminated its surroundings with steady light becomes the cradle of a black hole, an object that hides its interior from the outside universe while still exerting an unmistakable pull on everything around it. Observations of core collapse supernovae provide some of the clearest links between theory and reality in this chain of events, but they also reveal puzzles. Light curves show diverse shapes indicating that the explosions vary in strength and structure. Spectra reveal different chemical fingerprints tracking which layers of the star were ejected and which fell back. In at least one recorded case in the nearby Large Magellanic Cloud detectors on Earth measured a brief burst of neutrinos arriving just before the visible light from the supernova, confirming that neutrino emission plays a central role in the collapse. Yet detailed numerical models still struggle to reproduce every feature of observed explosions. Some simulated stars fail to explode and instead collapse all the way into black holes. Others explode too easily or with the wrong energies. These mismatches hint that important pieces of physics, perhaps related to turbulence, magnetic fields, or rotation, remain only partly understood. Thus, the death of a massive star stands at a boundary between well-tested nuclear physics and areas where current models are being refined. It is within this uncertain zone that the precise conditions for black hole birth are set, making every observed supernova and every failed explosion a valuable clue to how often gravity wins completely and locks matter away behind an event horizon. At the instant when a collapsing stellar core passes the critical threshold that turns it into a black hole, the familiar picture of matter and light moving through space begins to change in a fundamental way. Until this point, although conditions have been extreme, it has still been possible in principle for light and particles to escape from the central regions if they are moving fast enough and in a suitable direction. As the core contracts, however, there comes a moment when its radius shrinks below a particular value that depends only on its total mass and its rotation. At that radius, the escape speed from the surface equals the speed of light. If gravity continues to compress the core further, the escape speed from any point at or below this boundary becomes greater than the speed of light, which no known object or signal can reach. The surface defined by this condition is the event horizon. It is not a material shell, but a geometric boundary in space-time. Once formed, it separates events that can influence the outside universe from those that cannot. To an outside observer watching from a safe distance, the formation of the event horizon is not seen as a dramatic flash or a visible wall. Instead, the light from the last layers of matter hovering just above this boundary becomes more and more red-shifted, losing energy as it climbs out of the deepening gravitational well. Clocks attached to that infalling matter appear to slow their signals, spreading out over longer and longer intervals. In the most idealized models, the final approach to the event horizon takes an infinite time as seen from far away. The collapsing star seems to freeze and fade, never quite vanishing. Yet, from the point of view of the matter itself, the horizon is crossed in a finite proper time. The infalling layers do not experience an infinite delay. They move inward through the boundary without noticing any local sharp feature because the event horizon is defined globally by which paths light and particles are able to take, not by a sudden change in the local density or pressure. This difference between external appearance and internal experience is a direct consequence of the way gravity affects time in general relativity. It is already hinted at near less extreme objects such as white dwarfs and neutron stars, where strong gravity slows clocks slightly and bends light paths. Around a black hole, this effect becomes dominant. The region just outside the event horizon is a place where space and time are stretched and skewed so that spiraling orbits, delayed signals, and trapped paths are natural outcomes of the geometry. As the core continues to collapse behind the horizon, its details become hidden from observers outside. The no-hair theorems of classical general relativity state that after a period of adjustment, a stationary black hole can be completely described by only a few macroscopic quantities: its mass, its angular momentum, and, if present, its electric charge. All other information about the matter that formed it, such as its exact chemical composition or internal structure, is in this classical description lost to the outside world. Different stars with the same mass and spin can, through collapse, produce indistinguishable black holes. This apparent simplicity stands in contrast to the complex layered structures that preceded the collapse. A massive star spends millions of years building up a detailed internal profile only to have that structure erased in a fraction of a second once an event horizon forms. In numerical simulations, the forming black hole settles into a stable configuration by emitting gravitational waves and shedding irregularities. These waves carry away some information about the asymmetries in the collapse, but once they have passed, the remaining object has a clean, featureless exterior. The boundary of the event horizon marks a profound division in predictability. Outside, given the mass and spin of the black hole, general relativity allows precise calculation of orbital paths, time dilation factors, and light bending. The geometry is well defined, and the behavior of test particles is governed by clear equations. Inside those same equations extended naively predict that the matter continues collapsing until it reaches a region where densities and space-time curvature become infinite, a point-like singularity in the non-rotating case, or a more extended structure in rotating solutions. In either case, the laws of physics, as currently formulated, cease to give sensible answers. Calculations return divergences, and it is no longer clear what actually happens to the matter in this regime. Physicists interpret this not as evidence that nature contains true infinities, but as a signal that general relativity is being pushed beyond its domain of validity. To understand what takes place at the center of a black hole, a theory that combines general relativity with quantum mechanics would be needed. Such a theory, often called quantum gravity, remains incomplete. Meanwhile, the outside behavior of black holes is supported by an increasing body of observational evidence. In X-ray binary systems, a visible star orbits an unseen companion that is too massive and too compact to be a white dwarf or neutron star. Gas pulled from the visible star forms an accretion disk around the dark object. Friction and magnetic turbulence in the disk heat the gas to millions of degrees, causing it to emit X-rays. Detailed observations of these emissions, including their brightness variations and spectra match models in which the inner edge of the disk lies near the innermost stable circular orbit, a distance from the central mass that depends on the geometry of a black hole. In some systems, changes in the disk, brightness suggests that matter is plunging inward past this inner orbit, presumably crossing the event horizon. Thus, while the horizon itself cannot be seen directly, its presence is inferred from the way it limits stable orbits and allows matter to disappear without further radiation once it crosses a certain boundary. This agreement between theory and observation strengthens confidence in the overall picture of black hole formation even as the nature of the core remains uncertain. The birth of a black hole also leaves imprints in gravitational waves. When the collapsing core is asymmetric, or when a black hole merges with another compact object, the resulting space-time vibrations propagate outward at the speed of light. Facilities on Earth designed to detect such waves have already measured signals from merging black holes of stellar mass. The waveforms show a characteristic chirp and ringdown pattern that fits the predictions for black holes of particular masses and spins settling into a final state. These detections serve as an independent confirmation that objects with event horizons and strong space-time curvature exist in nature, formed through processes that involve gravitational collapse. They do not, however, reveal what happens once matter has passed the horizon. That interior remains sealed to any signal that could reach outside observers. The mismatch between the clean exterior description and the unknown interior fate of matter adds an element of mystery to the otherwise precise equations of general relativity. It raises questions about whether information is truly lost, how quantum fields behave near and inside the horizon, and whether new physics emerges at extremely small scales. Thus, the birth of a black hole is not only the endpoint of a stellar life, but also the starting point of a deeper tension between what current theories can describe and what they leave unexplained. Around a black hole, gravity does more than pull on matter. It shapes the very stage on which motion takes place. In general relativity, gravity is described as the curvature of space-time, the combined arena of space and time. A black hole is a region where this curvature becomes so intense that the usual intuition about straight lines, steady clocks, and open paths no longer works in the familiar way. A test particle, such as a small rock or a bit of gas, does not feel a force in the ordinary sense in free fall. It simply follows the straightest possible path through curved space-time, a path called a geodesic. However, because the geometry around a black hole is strongly warped, these geodesics can loop spiral or plunge inward in patterns that differ sharply from orbits in weaker fields. Far from the black hole, space-time is nearly flat, and orbits resemble those in a planetary system around a star. Closer-in effects predicted by general relativity become important. One such effect is the precession of orbits. In a simple Newtonian model, an object in an elliptical orbit around a central mass repeats the same path endlessly. In a strongly curved space-time, the ellipse rotates slowly so that each orbit is slightly shifted. This kind of precession is seen in the motion of planets around stars, for example, in the perihelion advance of Mercury, and it becomes far more pronounced near compact objects. Near a non-rotating black hole, there exists an innermost stable circular orbit for massive particles. At greater distances, a particle can remain on a circular path. Slight perturbations cause gentle oscillations, but do not necessarily lead to a plunge. At radii closer than this special orbit, no stable circular paths exist. A small disturbance there sends the particle spiraling inward toward the event horizon. In the theory of a rotating black hole, called a Kerr black hole, the structure is more intricate. The space-time frame itself is dragged around by the rotation, an effect known as frame dragging. Particles and light are compelled to swirl in the direction of the spin if they venture too close. The region where this effect is strong enough that no object can remain at rest with respect to distant stars is called the ergosphere. Within the ergosphere, but outside the event horizon, escape to infinity is still possible, but only through motion that respects the local dragging of space-time. These effects are not just mathematical constructs. They influence how gas moves in the accretion disks that feed many black holes. Observations in X-rays and other wavelengths show that matter in such disks reaches orbital speeds of a significant fraction of the speed of light near the inner edge. The radiation emitted carries imprints of the orbital structure. For instance, the iron emission lines seen in X-ray spectra from some accreting black holes are broadened and skewed in ways that match predictions from disks orbiting close to the innermost stable circular orbit. The red wing of the line extends far to lower energies, a sign that photons have lost energy while climbing out of a deep gravitational potential. Time dilation is another central feature of the gravity well around a black hole. In general relativity, a clock deeper in a gravitational field ticks more slowly relative to a clock at a higher potential. For black holes, this effect becomes extreme. A clock orbiting near the innermost stable circular orbit runs significantly slower than one far away. Signals sent from this region to distant observers are delayed and redshifted. In certain galactic centers, stars orbit close enough to their central supermassive black holes that their motion shows measurable relativistic effects. Long-term monitoring of one particular star near the center of the Milky Way has revealed both its strong gravitational redshift at closest approach and the precession of its orbit over time. These observations serve as direct tests of the space-time curvature close to a supermassive black hole, confirming that the gravitational potential there is both deep and compact. Light itself follows curved paths near a black hole. Photons that pass at large distances are only slightly deflected, but those that skim closer to the event horizon can be bent by large angles. Some can loop around the black hole one or more times before escaping, forming a narrow set of paths associated with the so-called photon sphere. In principle, an observer with perfect instruments and alignment could see multiple images of the same background object, each corresponding to light that has completed a different number of loops. In practice, these higher-order images are faint and difficult to resolve, but their existence emerges naturally from the equations. The overall effect of light bending by mass is called gravitational lensing. Around black holes, this lensing can produce a bright thin ring of light from surrounding emission if seen from afar. When international collaborations used very long baseline radio interferometry to image the region around the supermassive black hole in the galaxy M87, the resulting picture showed a dark central depression surrounded by a bright asymmetric ring. The size and shape of this structure match expectations for emission from matter near a photon orbit, lensed by a central black hole with a particular mass and spin. Thus, what is seen is not the event horizon itself, but the shadow it casts on the glowing material around it, shaped by space-time curvature. The gravity well also affects how magnetic fields and plasma behave. In many accreting systems, powerful narrow jets of plasma emerge from the regions near the black hole, extending for vast distances into interstellar or even intergalactic space. The precise mechanism that launches and collimates these jets remains an active area of research, but many models rely on the twisting of magnetic field lines in the rotating spacetime near the event horizon and the ergosphere. Rotational energy from the black hole and energy from the accretion disk may be tapped to power these outflows. The alignment and stability of the jets over long timescales hint at an underlying structure imposed by the gravitational and magnetic field configuration, yet the details of how particles are accelerated to high energies and guided into such narrow beams are still being refined. One of the striking features of the gravity well is how it couples different kinds of measurements into a coherent picture while leaving open questions at the extremes. Orbital dynamics reveal the mass and compactness of the central object. Spectral features from accretion disks encode information about velocities and gravitational redshifts. Direct imaging with radio interferometry traces light bending and the outline of the central shadow. Gravitational wave observations from mergers probe the response of space-time itself when black holes collide and settle. Together, these diverse data streams converge on the same basic parameters for known black holes and match general relativistic predictions with impressive accuracy in the regimes that can be observed. Yet very close to the horizon, particularly for smaller stellar mass black holes, direct observation becomes nearly impossible with current instruments. The smallest scales and highest curvatures remain hidden. Models of how matter behaves in this environment, including turbulent flows, shock heating, and particle acceleration, rely on complex numerical simulations that must approximate certain physical processes. Differences among simulation methods and assumptions can lead to differences in predicted brightness patterns, variability, and jet properties. Comparing these theoretical predictions with observations often highlights small discrepancies, suggesting that the understanding of how matter and fields interact with the gravity well near the horizon is still incomplete. The gravity well around a black hole thus stands as both a well-tested laboratory for general relativity and a frontier where subtle departures from expectations could reveal new physics. Any small mismatch between predicted and observed motion spectra or images in the deep potential could signal additional effects, perhaps from quantum corrections or from interactions between dark matter and the central mass. So far, general relativity has passed every test in this regime, but the precision of measurements continues to improve. Each new orbit mapped each new image taken, and each new flare recorded near a black hole adds another piece to the pattern of how spacetime behaves under extreme curvature, and each such piece is examined for signs that the gravity well hides more than the current equations admit. Near a black hole, the journey of an infalling traveler offers a clear way to link abstract theory with concrete experience. Consider a small spacecraft that begins far from the black hole where space is nearly flat and time flows at a rate that matches clocks in the wider universe. At first, the craft orbits in a region where the gravitational field is strong but not yet extreme. Instruments record a steady pull, and navigational systems correct for orbital precession and light bending using well-tested formulas from general relativity. As the craft fires its engines to spiral inward, the gravitational acceleration grows. The path tightens into a faster orbit, and the time between successive passes around the black hole shrinks according to the craft's own clock. To an external observer watching from a distant fixed platform, this motion already appears altered. Signals from the spacecraft take longer to arrive and are slightly redshifted, carrying less energy than when they were sent. Both effects arise because the craft is climbing out of a deeper gravitational potential after each orbit. Still, at these moderate distances, communication remains practical, and the differences in clock rates can be calculated and verified. The picture changes as the spacecraft approaches the innermost stable circular orbit. Here, small adjustments in thrust can no longer hold a perfectly circular path for long. Any tiny perturbation causes the orbit to spiral inward. If the pilot decides to maintain free fall and shuts off the engines, the craft begins a plunge toward the event horizon. Its velocity relative to the distant observer increases, approaching a significant fraction of the speed of light. Signals sent outward become more infrequent and more redshifted. From the distant viewpoint, each pulse arrives after a longer delay and at a lower frequency. The craft seems to slow and fade as it nears the horizon, its last signals stretching over an ever-lengthening interval. In idealized models, the approach to the event horizon takes an infinite amount of time as measured by the distant clock. The traveler appears to freeze just above the boundary and then gradually fades from view as the redshift pushes the emission beyond detectability. Inside the spacecraft, the onboard clock tells a different story. The crew's subjective time remains well behaved. They do not feel their own clock slowing. Instead, they may see the outside universe speed up. Light from distant galaxies, if visible through appropriate instruments, arrives in a pattern that reflects the accelerated ticking of external clocks. Events that would have taken place over long periods in the outside cosmos can in principle be seen to unfold much more rapidly as the craft descends deeper into the gravitational well. This disparity between perspectives is a central feature of the geometry around a black hole. In practice, real infalling matter is unlikely to be an intact spacecraft. Gas clouds, dust, and fragmented stellar material follow complex paths that include shocks, turbulence, and interactions with magnetic fields. However, the core ideas about how time and light behave still apply. Just outside the event horizon, tidal forces begin to grow important. Tidal forces arise because gravity is stronger on the nearer side of an extended object than on the farther side. Around Earth, tidal effects from the Moon subtly lift and lower oceans. Around a stellar mass black hole, the gradient in gravity near the horizon is far more intense. For a human-sized traveler approaching such a black hole, the difference in gravitational pull between head and feet could reach destructive levels well before the horizon is crossed. The body would experience stretching along the direction toward the black hole and compression in the perpendicular directions. In popular descriptions, this process is often called spaghettification. For a small black hole, tidal disruption can occur outside the event horizon, ensuring that no intact object reaches the boundary. For a supermassive black hole with a mass millions of times greater than that of the Sun, the situation is different. The horizon lies much farther from the central singularity, and the gravitational gradient at that radius is gentler. In such a case, an object of modest size could potentially cross the event horizon without being torn apart immediately. Tidal forces would still be present and would increase as the fall continues, but the fatal stretching and compression could be delayed until deep inside. How long any complex structure survives depends on the mass of the black hole and on the trajectory. Classical general relativity predicts that once across the horizon, all paths lead inevitably inward. Time and space swap roles in a specific technical sense. For an infalling traveler, moving away from the singularity would no longer be an available option, much as moving backward in time is not allowed in ordinary experience. The interior region becomes a one-way route toward increasing curvature and density. Yet some theoretical proposals suggest additional features may appear near the horizon when quantum effects are taken into account. One such idea is the notion of a firewall, a hypothetical layer of very high energy quanta at or near the event horizon that would destroy any infalling matter almost instantly. This concept arises from attempts to resolve the tension between general relativity, which treats the horizon as locally unremarkable for freely falling observers, and quantum mechanics, which raises puzzles about information loss. At present, no observational evidence directly supports the existence of firewalls, and they remain one of several competing ideas. Another line of reasoning suggests that subtle quantum correlations in the radiation emitted by black holes might preserve information without introducing violent effects at the horizon. In that view, the classical picture of a smooth passage across the horizon remains valid, but the underlying quantum description is more intricate than standard calculations suggest. As with many aspects of black hole physics, the difference between these pictures is hidden behind observational limits. Instruments cannot yet probe the horizon region with sufficient detail to distinguish between a sharply disruptive boundary and a smooth one. For astrophysical black holes, the light that comes from just outside the horizon is blended with emission from the accretion disk and any surrounding plasma. Timing measurements and spectral analysis can reveal the gravitational redshift and orbital dynamics, but they do not yet show whether any additional structure exists exactly at the horizon. Gravitational wave signals from merging black holes carry information about the way the horizons deform and ring down, but current detections match the smooth behavior predicted by general relativity to within measurement errors. Thus, the experiences of any hypothetical infalling traveler, including whether they encounter a calm crossing or a sudden destruction at the boundary, remain a matter of theoretical debate rather than empirical fact. What is firmly established is the extreme nature of time dilation, redshift, and tidal forces near the horizon and inside it. These effects together mean that from the perspective of the wider universe, infalling matter appears to approach the horizon and slowly vanish, while from its own perspective it crosses the boundary without fanfare and then faces increasing curvature that classical theory cannot fully describe. The approach to the event horizon thus stands as a region where calculations are precise but interpretations diverge, where a simple geometric surface separates the part of spacetime that can be observed from the part that remains permanently out of reach, and where even the fate of information itself is an open question awaiting deeper understanding. Deep inside a black hole beyond the region that any signal can leave the classical description of spacetime reaches its limit. General relativity, the theory that has successfully described gravity from the solar system's scale to the scale of galaxies and the expanding universe, offers precise equations for how matter and curvature influence each other. When these equations are applied to a sufficiently massive collapsing object, they predict that the inward fall of matter behind the event horizon does not halt at any finite density. Instead, the curvature of spacetime and the density of energy increase without bound as the collapse proceeds. In the simplest solutions for a non-rotating black hole, all of the mass is compressed into a point of zero volume and infinite density called a singularity. In rotating solutions, the structure is more extended, but still involves regions where quantities in the equations diverge. These divergences are not so much a physical picture as a sign that the theory is being pushed beyond the domain in which it can give reliable answers. They resemble in mathematical form the way a calculation breaks down when a term that requires division by zero appears. The singularity is in this sense less an object and more a boundary of understanding. The path to this boundary, according to the classical picture, is unidirectional for any matter that has crossed the horizon. The geometry inside the horizon is such that moving away from the singularity would require motion faster than light, which is not allowed. All time-like paths, those followed by matter with mass, and all light-like paths, those followed by radiation, curve toward the central region. For an infalling particle, there is no choice of thrust or orientation that can avoid the encounter once the horizon has been crossed. The proper time between crossing the horizon and reaching the singularity is finite, and for stellar mass, black holes quite short. This inevitability raises an immediate conceptual problem. Ordinary matter carries many types of information in the sense that it has detailed internal structure. Atoms have specific arrangements of protons, neutrons, and electrons. Complex objects have particular shapes, compositions, and states. When such matter falls into a black hole, the external description of the black hole, after it has settled down, contains only mass angular momentum and possibly electric charge. All other details appear to be erased from the outside view. If the mass of the black hole later changes, for instance, through the slow process of Hawking radiation, the outgoing particles seem to carry no memory of the specific information that went in. This apparent mismatch between the detailed information content of initial matter and the sparse description of the final radiation is known as the information loss problem. In ordinary quantum mechanics, the evolution of an isolated system is reversible in principle. Knowing the complete state at one time allows reconstruction of the state at an earlier time, at least in theory. If black holes simply swallow information at the singularity and later evaporate into featureless radiation, that reversibility would be broken. The state of the universe at a later time would not contain enough information to reconstruct the earlier state, even in principle. This tension between the reversibility of quantum mechanics and the behavior of black holes, as predicted by classical general relativity and Hawking's calculations, is one of the central puzzles in fundamental physics. Various approaches attempt to address it. Some propose that subtle correlations in the Hawking radiation encode the missing information in a way that is not captured by the earliest calculations. Others suggest that the description of space-time inside and outside the horizon must be modified at very small scales so that no true singularity forms and no information is irretrievably lost. In string theory and related frameworks, for example, space-time and matter are built from more basic constituents that may smear out the singularity and replace it with a region of very high but finite density. In loop quantum gravity models, the discrete structure of space-time at the smallest scales may prevent infinite curvature and allow a bounce or transition to another phase. At present, none of these ideas has been tested in regimes where clear observational signatures are available, but they provide examples of how the singularity might be resolved once a full theory of quantum gravity is developed. Observationally, the singularity itself remains inaccessible. No signal can emerge from the region where classical theory predicts its existence. All evidence about what happens inside a black hole must therefore be indirect inferred from the behavior of matter and fields just outside the horizon and from global consistency requirements on the laws of physics. This limitation does not render the question irrelevant. Instead, it turns the singularity into a sensitive probe of how well current theories fit together. Whenever general relativity and quantum mechanics are both important, as near the singularity, any inconsistency or incompleteness in their combination is likely to be revealed in the form of paradoxes. The information loss problem is one example. Another appears when attempting to calculate the entropy of a black hole, a measure of the number of microscopic states that correspond to the same macroscopic parameters. Classical general relativity suggests that the entropy is proportional to the area of the event horizon rather than the volume inside it. This surprising result extended and refined through later work hints that the fundamental description of spacetime might in some sense be holographic, with the information content of a region encoded on a lower dimensional boundary. Such ideas have inspired models in which the interior of a black hole is represented by degrees of freedom, living on or near the horizon, blurring the distinction between inside and outside in a way that may remove the need for a singular core. Still, these models are largely theoretical constructions, tested mainly through their internal consistency and through analogies with other systems, rather than through direct measurement. The singularity also plays a role in cosmological thinking. The equations that predict a singularity at the center of a black hole are closely related to those that, when applied to the entire universe, predict a singular starting point in the past, sometimes called the Big Bang singularity. In both cases, the presence of a singularity signals that the theory being used cannot be extrapolated beyond a certain point. Just as the interior of a black hole calls for quantum gravity, the earliest moments of the universe likely do as well. Any successful theory that resolves one of these singularities is expected to shed light on the other. This link increases the importance of understanding what really happens in the deepest interior of a black hole. because progress there may inform models of cosmic origins and vice versa. Numerically, simulations of gravitational collapse do not directly reach the singularity. Instead, they follow the evolution until densities become extremely high, then either terminate or use methods that effectively remove the singular region while maintaining the influence of its mass on the surrounding spacetime. From the point of view of an external observer, this is sufficient because the gravitational field outside the horizon depends only on the total mass and spin, not on the detailed structure of the core. However, from a theoretical perspective, simply excising the singularity leaves unanswered questions about the ultimate fate of matter and information. Some researchers explore the possibility that the interior of a black hole may connect to another region of spacetime, perhaps via a structure sometimes called a wormhole. In certain exact solutions of the equations, such connections exist, but they are typically unstable and require idealized conditions. Quantum effects may alter this picture, either stabilizing or further destabilizing such structures. At present, the existence of traversable connections of this kind in realistic black holes remains speculative. Nonetheless, the idea that the singularity might be replaced by a bridge to another domain or by a region in which spacetime itself has a different character illustrates how black holes push thinking beyond the familiar. The enigma of the singularity thus lies in the intersection of several threads. Classical theory predicts its existence, but also signals its own breakdown there. Quantum theory demands that information be preserved, but offers no complete account of how this happens when matter falls into a region from which no signal can escape. Observations confirm the presence of horizons and strong curvature, but cannot peer into the interior. Between these constraints, models of the core of a black hole remain imaginative yet grounded attempts to extend known physics into an extreme regime. Each new insight into quantum fields in curved spacetime, each improvement in understanding the microscopic origin of black hole entropy, and each test of gravitational behavior near horizons contributes to narrowing the space of possibilities. But the central question of what if anything replaces the classical singularity remains open. At the centers of many galaxies, including the Milky Way, lie objects far more massive than the black holes formed from single collapsing stars. These supermassive black holes contain millions to billions of times the mass of the Sun in a region smaller than the orbit of the outer planets. Their presence is not inferred from a single line of evidence, but from a convergence of different observations that, taken together, leave little room for alternative explanations. In the Milky Way, radio and infrared telescopes operated by observatories around the world have tracked the motion of individual stars near the galactic center for decades. These stars follow elongated paths that bring them very close to an unseen central mass before they swing back out. By measuring their positions and velocities over time, astronomers reconstruct their orbits and determine how much mass must be concentrated in the small volume they circle. The result points to a compact object with a mass equivalent to several million suns confined within a region smaller than the orbit of Mercury. No cluster of normal stars, stellar remnants, or dense gas could remain so compact without collapsing, leaving a supermassive black hole, often referred to as Sagittarius A star, as the most consistent interpretation. In other galaxies, the evidence takes different forms. In some spiral galaxies, radio observations of water maser emission, a natural amplification of microwave radiation by molecules in orbit around the nucleus, reveal a thin rotating disk. The velocities of the maser spots mapped with high precision indicate that they are moving under the gravitational influence of a central object much more massive than any known stellar cluster, again supporting the presence of a supermassive black hole. In galaxies classified as active, the central regions shine with extraordinary brightness across a wide range of wavelengths, from radio waves to X-rays and sometimes gamma rays. The light output from these active galactic nuclei often exceeds that of all the stars in the host galaxy combined. Variability on short timescales suggests that the emitting region is very compact because large structures cannot brighten or dim coherently in such a short time. The broad emission lines seen in their spectra indicate gas moving at high speeds close to the central engine. Models in which matter accretes onto a supermassive black hole forming a hot disk and corona successfully reproduce many of these features. The efficiency of energy release in such accretion flows where a significant fraction of the rest mass energy of infalling matter can be converted into radiation, explains how a relatively modest rate of mass inflow can power the enormous luminosities of quasars and other active nuclei. Direct imaging has added a new layer of confirmation. The Event Horizon Telescope collaboration using very long baseline radio interferometry to combine data from widely separated antennas has produced images of the emission near the supermassive black hole in the center of the galaxy M87 and later of Sagittarius A star itself. These images show a bright asymmetric ring surrounding a dark central region. The size of the ring, when compared to the mass inferred from stellar motions and gas dynamics, matches the expected scale of the photon orbit around a black hole. The shape and brightness distribution of the ring fit models of light, bending in a curved spacetime where emission from the accretion flow is lensed into a crescent by the intense gravity. The dark region at the center is not the event horizon itself, but the shadow cast by the black hole on the surrounding glow. Its size and form provide one of the most direct visual confirmations yet of the existence of a deep gravitational well consistent with general relativity. Supermassive black holes do not simply sit at the centers of galaxies. They interact with their surroundings in ways that can influence the structure and evolution of their hosts. Gas that falls toward the central regions can form a rotating disk heat up through friction and magnetic turbulence and radiate energy. In some systems, a fraction of the inflowing material and energy is redirected into collimated jets that emerge along the rotational axis. These jets extend for thousands or even millions of light years, piercing the surrounding interstellar and intergalactic medium. Observations show that the jets inflate large lobes of radio-emitting plasma and can heat or displace gas on galactic and cluster scales. This activity, often called feedback, can regulate star formation by preventing gas from cooling and condensing in the usual way. In galaxy clusters, X-ray observations reveal cavities in the hot intracluster gas carved out by the work done by radiojets from central active galaxies. The balance between heating by jets and cooling by radiation appears in some cases to maintain the gas in a quasi-stable state, slowing the formation of new stars and altering the long-term evolution of the cluster. The link between supermassive black holes and their host galaxies extends beyond such direct interactions. Surveys of nearby galaxies have revealed empirical correlations between the mass of the central black hole and properties of the galactic bulge, such as the velocity dispersion of stars or the total stellar mass. These correlations suggest that the growth of black holes and the assembly of galaxies are not independent processes. Somehow, over cosmic time, the mass of the central object and the stellar component have become closely coupled, even though the black hole accounts for only a small fraction of the total mass in stars. The mechanisms that produce this coevolution likely involve the inflow and outflow of gas merger histories and feedback from active galactic nuclei, but the details remain under study. Observations of very distant quasars whose light has taken most of the age of the universe to reach us add another layer of mystery. Some of these quasars host black holes with masses of billions of solar masses when the universe was still less than 1 billion years old. Standard models of black hole growth, in which stellar mass seeds gradually accumulate mass through accretion and mergers, struggle to reach such large masses in the available time without invoking unusually high growth rates that persist for long intervals. This tension has led to suggestions that at least some supermassive black holes may have formed from heavier seeds, perhaps through the direct collapse of massive gas clouds or through dense clusters of stars that rapidly merged into intermediate mass black holes before growing further. Each proposed pathway has its challenges and observational signatures. The relative importance of these channels remains uncertain, and new surveys aiming to detect intermediate mass black holes may help distinguish among them. The precise structure of the gas and dust around supermassive black holes also shows complexity. Infrared and X-ray observations indicate the presence of obscuring material in some active nuclei, sometimes organized in a thick torus-like distribution that can block direct views of the central engine along certain lines of sight. This geometry helps explain why some active galactic nuclei appear bright in certain wavebands, but dim or hidden in others, depending on orientation. However, high-resolution observations reveal clumpy and dynamic structures rather than simple uniform shapes. The interplay between inflowing gas, outflowing winds, radiation pressure, and magnetic fields shapes these central regions in ways that are still being mapped in detail. Supermassive black holes therefore occupy a dual role. They are compact extreme objects that provide testing grounds for gravity in the strong field regime, and they are central components in the ecosystems of galaxies, influencing star formation gas dynamics and large-scale structure. At the same time, their origins and early growth remain only partly understood. The question of how the first massive seeds formed in the young universe, how quickly they accreted, and how they affected their environments while doing so is an active frontier in both observation and theory. Deep surveys with space-based and ground-based observatories continue to push the detection of quasars and active galactic nuclei to earlier cosmic times, while numerical simulations attempt to follow the coupled evolution of galaxies and their central black holes from the first stars to the present day. Each new detection of a distant luminous quasar or a quiet massive black hole in a nearby galaxy adds another data point to this picture, sometimes reinforcing existing models and sometimes revealing outliers that require new explanations. The apparent regularity of the correlations between black hole mass and galactic properties suggests an underlying order, yet individual systems with unusually massive or unusually small central black holes relative to their hosts demonstrate that this order is not absolute. In these exceptions, astronomers look for clues about different growth histories or environmental conditions that might have led to divergent outcomes. Whether the observed relationships reflect a fundamental law of galaxy formation or an emergent pattern arising from many interacting processes remains an open question. In this way, supermassive black holes stand both as anchors in galactic centers and as markers of cosmic history. Their present masses and activity levels encode information about past inflows of gas, past mergers with other galaxies, and the balance of feeding and feedback over billions of years. Reading that record requires careful interpretation, and in doing so, astrophysicists find themselves returning to the same underlying puzzle: how objects that trap light and hide their interiors can still shape the visible universe on the largest scales, and how their quiet gravitational influence and their occasional bright outbursts together trace a story that is still incomplete. Black holes do not only form in isolation, they also grow and interact over cosmic time. A stellar mass black hole born from the collapse of a single massive star can increase its mass by accreting gas from its surroundings or by merging with other compact objects. In a binary system where a normal star orbits a black hole, gas can be pulled from the companion and form an accretion disk around the black hole. As this material spirals inward, it radiates energy and gradually adds to the mass of the central object. Over millions of years, such accretion can significantly change the black hole's mass, although feedback from radiation and outflows often limits the rate. In dense stellar environments, such as the cores of globular clusters or young massive star clusters, close encounters can assemble binaries containing two compact objects, two black holes or a black hole, and a neutron star. These pairs orbit each other under their mutual gravity. As they do so, they emit gravitational waves, ripples in space-time that carry energy away. The emission is initially weak, but over long periods it causes the orbit to shrink and the orbital period to decrease. The pair gradually spirals toward coalescence. The rate of this spiral depends strongly on the separation and masses of the objects. Wide binaries can persist for times longer than the age of the universe without merging, while close binaries can coalesce within a fraction of that time. Theoretical models of stellar evolution and cluster dynamics predict a population of such merging systems distributed across cosmic history. For a long time, these predictions could not be tested directly. Indirect evidence came from X-ray binaries, where one member is a compact object accreting from a companion and from the absence or presence of certain types of supernova remnants. The advent of gravitational wave astronomy changed this situation. Large ground-based interferometric detectors using laser beams along arms several kilometers long to measure tiny changes in distance began operating with sufficient sensitivity to detect gravitational waves from mergers of stellar mass black holes. The first confirmed signal revealed the coalescence of two black holes, each with masses several tens of times that of the Sun at a distance of more than 1 billion light-years. The waveform of the signal matched detailed numerical relativity calculations of two black holes in spiraling merging and then settling into a single, more massive black hole that undergoes a brief phase of damped oscillation. Since that first detection, dozens of further events have been recorded, including mergers of black holes with a range of masses and systems involving at least one neutron star. The observed population has already revealed surprises. Some detected black holes are more massive than those commonly inferred from X-ray binaries, suggesting that formation channels in certain low metallicity environments can produce unusually heavy stellar remnants. The distribution of spin magnitudes and orientations hints at multiple formation pathways. Some binaries may have evolved from pairs of massive stars that formed together and remained bound, while others may have been assembled dynamically in dense clusters through gravitational encounters. Each event adds to a growing catalog that is used to infer the underlying population of black holes in the universe. The gravitational wave signals carry information not only about the component masses and spins, but also about the properties of space-time itself in the strong field regime near the merging horizons. The late stage of the signal, when the newly formed black hole settles, depends sensitively on the parameters of the final object. Comparing the observed ringdown with predictions from general relativity tests, whether the black hole is described by the expected solutions. So far, within measurement uncertainties, the signals agree with the theory. No clear deviations have been detected, but as detector sensitivities improve, small differences may become observable, offering a possible window into new physics. Black hole mergers also have consequences for the environments in which they occur. When two black holes coalesce, the gravitational waves they emit carry momentum as well as energy. If the emission is not perfectly symmetric, the remnant black hole receives a recoil kick. Calculations show that in some configurations, the kick velocity can be large enough to eject the remnant from a globular cluster or even from the shallow potential well of a small galaxy. Observational hints of displaced or off-center black holes in some systems may be related to such processes, although other explanations such as asymmetric gas dynamics are also possible. If recoil kicks are common, some galaxies may lose part of their population of stellar mass or intermediate mass black holes over time, altering the way these objects are distributed in the universe. On larger scales, mergers between entire galaxies bring their central supermassive black holes together. As galaxies merge, dynamical friction against stars and gas causes the black holes to sink toward the center of the newly formed system. Once the two black holes form a bound pair, further interactions with stars and gas can harden the binary, shrinking its separation. Eventually, at small enough distances, gravitational wave emission dominates the evolution and drives the pair toward coalescence. The final merger of supermassive black holes emits gravitational waves at much lower frequencies than those produced by stellar mass binaries, with periods of years to hours rather than fractions of a second. These low-frequency waves are beyond the reach of current ground-based detectors, but they may be detectable by other methods. One approach uses a network of millisecond pulsars rapidly rotating neutron stars whose radio pulses reach Earth with remarkably stable timing. A passing gravitational wave can introduce tiny correlated shifts in the arrival times of pulses from many such objects across the sky. Recent analyses of pulsar timing data have reported evidence for a common background of low-frequency gravitational waves consistent with signals from a large population of distant supermassive black hole binaries. Space-based detectors planned for the future aim to measure individual mergers in this regime using laser interferometry over millions of kilometers. If successful, such observations would open a new window on the assembly history of galaxies and their central black holes. Growth through accretion and mergers leads naturally to questions about the full spectrum of black hole masses. Observations clearly reveal stellar mass black holes and supermassive black holes, and there are candidates for intermediate mass black holes with masses between these extremes. The existence and number of such intermediate objects remains uncertain, in part because their observational signatures can be subtle. They are massive enough that their accretion luminosity can be drowned out by other activity in galactic centers, yet not so massive as to dominate the dynamics on large scales. Identifying them relies on careful dynamical measurements in star clusters or on X-ray observations of unusually bright sources that might be powered by accretion onto an intermediate mass black hole. Theoretical models suggest that these objects could form through repeated mergers in dense clusters or through the collapse of massive star clusters, but definitive examples are still rare. Even more speculative is the idea that some black holes might be primordial, formed not from stars, but from density fluctuations in the early universe. In certain scenarios, regions of slightly higher density soon after the Big Bang could have collapsed directly into black holes of various masses. Such primordial black holes, if they exist in significant numbers, could contribute to the dark matter or influence the formation of structure. Constraints from microlensing surveys the cosmic microwave background, and other observations already rule out primordial black holes as the dominant form of dark matter across many mass ranges, but small allowed windows remain. Gravitational wave observations have been used to test whether some merging black hole pairs could be primordial rather than stellar in origin. So far, the events are consistent with stellar formation channels, but the possibility of a minor primordial component is not excluded. In this way, the study of black hole mergers intersects with broader questions about the composition of the universe. The pattern of detected events, including their masses, spins, and redshift distribution, is compared against models that assume different formation scenarios. Any significant excess of mergers with properties difficult to explain through stellar evolution could hint at an additional population. Conversely, agreement with stellar models tightens constraints on more exotic possibilities. The interplay between theory and observation here is dynamic. As detectors become more sensitive and cover a wider frequency range, they will sample more of the merger population, potentially revealing rare types of events. Black hole mergers also act as beacons that trace the growth of structure over time. The rate of mergers at different cosmic epochs reflects the history of star formation, the assembly of galaxies, and the conditions in dense stellar systems. By measuring this rate as a function of redshift, astrophysicists can cross-check other probes of cosmic history, such as galaxy surveys and measurements of the background radiation. Any mismatch between the inferred merger history and expectations from other data may point to missing ingredients in the understanding of how black holes form and grow. Thus, the growth and merging of black holes form a network of clues that link the life cycles of individual stars to the evolution of galaxies and the large-scale structure of the universe. Each observed merger encapsulates a long history of stellar birth evolution and interaction compressed into a brief burst of gravitational waves. Each undetected or rare type of event, such as the merger of two intermediate mass black holes or of two very rapidly spinning black holes, represents a gap in current knowledge. Filling these gaps will require not only more sensitive instruments, but also more detailed models of how black holes populate different environments and how they interact with the gas in stars around them. In the meantime, the emerging picture is that the universe contains far more black holes than can be seen, directly many of them, in binaries slowly emitting gravitational waves too weak to detect at present. These hidden pairs scattered through galaxies and clusters form an unseen background of activity, shaping the distribution of mass and the future potential for louder detectable mergers. The visible signals that have already been measured are thus only the bright nearby examples of a much broader, largely invisible process that continues throughout cosmic time. On the largest timescales that can be meaningfully discussed, black holes are not permanent fixtures, but slowly changing participants in the thermal history of the universe. In classical general relativity, a black hole that does not accrete additional matter or merge with other objects retains a fixed mass and a fixed horizon area. It simply sits, influencing its surroundings only through gravity. Quantum field theory in curved space-time modifies this picture. When quantum effects are taken into account near the event horizon, a solitary black hole is predicted to emit radiation, a process known as Hawking radiation. This radiation allows the black hole to lose energy and mass over time. The starting point for this idea is that what is called empty space is not truly empty. Even in a vacuum, quantum fields fluctuate. Pairs of particles and antiparticles briefly appear and annihilate a constant background of virtual activity. Near the event horizon of a black hole, the curved spacetime affects how these fluctuations behave. In Hawking's calculation, the presence of the horizon changes the structure of the quantum fields in such a way that when the situation is viewed from far away, there is a steady flux of real particles streaming outward. These particles carry away energy. Conservation of energy requires that the black hole's mass decrease correspondingly. A few simple statements capture the main consequences. A black hole has an effective temperature inversely related to its mass. Smaller black holes are hotter and radiate more strongly, while very massive black holes have extremely low temperatures and radiate exceedingly slowly. For a black hole with a mass comparable to that of the Sun, the Hawking temperature is far below the cosmic microwave background temperature that fills the universe, so such a black hole would gain energy from the background rather than lose it at present. Only when the universe has cooled much further and when other sources of accretion have dwindled would Hawking radiation become the dominant process. For supermassive black holes in galactic centers, the temperatures are even lower, effectively zero, on ordinary scales. Nevertheless, over sufficiently long times, even these giants are predicted to evaporate. The timescales involved are immense. The lifetime of a black hole due to Hawking radiation grows rapidly with its mass. A stellar mass black hole would require far longer than the current age of the universe to evaporate completely. A supermassive black hole with millions or billions of solar masses would persist for periods that exceed by huge factors any times now probed by observations. In this sense, Hawking evaporation is not relevant for the dynamics of galaxies or for the current era of cosmic evolution. It becomes important in thought experiments that project the universe far into the future, well beyond the lifetimes of stars and galaxies as they are now known. In such scenarios, after the last stars have burned out and normal matter has dispersed, black holes would remain as some of the final structured objects. Over many orders of magnitude in time, they would slowly lose mass through Hawking radiation, warming slightly as they shrink. Eventually, once they reach much smaller masses, their temperatures would rise enough that their remaining mass would be radiated away in a final brief burst of high-energy particles. No direct observational evidence for Hawking radiation has been obtained from astrophysical black holes, and such detection is beyond current capabilities. The predicted flux from known black holes is far too low to stand out against other sources of radiation. However, the underlying ideas are supported by the broader framework of quantum field theory in curved spacetime and by analog models in which systems with effective horizons show emission with similar characteristics. These analogs are not black holes, and their horizons are not gravitational, but they suggest that the essential mechanism is robust. The existence of Hawking radiation also connects with the notion of black hole entropy and temperature in a deeper way. In thermodynamics, systems with a temperature emit thermal radiation and possess an entropy that measures their microscopic degrees of freedom. Black holes, once quantum effects are included, behave as thermodynamic objects. Their temperature is associated with Hawking radiation, and their entropy is proportional to the area of the event horizon. This area law is unusual because most systems have entropy that scales with volume. The fact that black hole entropy scales with area has led to speculations that the fundamental information content of spacetime may itself obey a holographic principle in which a volume can be described by degrees of freedom on its boundary. Whether this interpretation is correct remains under investigation, but it provides a conceptual link between gravity quantum mechanics and information theory. In the far future, if Hawking radiation proceeds as currently understood, the universe enters an era in which black holes dominate the remaining structure. Ordinary stars have long since ceased to shine. White dwarfs, neutron stars, and stellar remnants cool or decay. Isolated planets drift. The main remaining sources of light and activity are rare accretion events as compact objects occasionally capture stray matter and the extremely slow evaporation of black holes. Over time, more and more black holes complete their evaporation and vanish, leaving only their emitted radiation and any surviving low-mass particles. The cosmos becomes increasingly dilute and homogeneous. At these stages, many familiar structures used to describe astrophysical systems lose their meaning. Galaxies have dispersed, clusters have dissolved, and the idea of a sky filled with stars no longer applies. Even in these remote epochs, questions about black holes remain central. Does the Hawking radiation carry all the information about what fell in, encoded in correlations so subtle that they are practically impossible to reconstruct, or is some information truly lost? Do quantum gravitational effects modify the final stages of evaporation, perhaps leaving stable remnants or altering the spectrum of emitted particles? Are there processes that could recycle or reconfigure spacetime in ways that current models do not capture? The answers are not yet known. Black hole evaporation, while grounded in well-established theoretical frameworks, stands at the edge of what can be tested. It connects the behavior of quantum fields in curved spacetime with the thermodynamic description of gravity and with the ultimate fate of structure in the universe. For now, the best supported view is that given enough time and an absence of fresh infall black holes slowly radiate away their mass, leaving a colder, emptier universe behind, even as the detailed bookkeeping of information in that process remains an unresolved part of the larger mystery. Black holes bring several lines of inquiry together into a set of puzzles that are not yet resolved, centered on the question of what happens to information and whether any deep connection exists between Horizon's quantum theory and possible hidden regions of spacetime. The information problem first raised in the context of black hole evaporation illustrates this tension. On one side stands the classical description from general relativity, in which matter and radiation that fall past the event horizon are cut off from the external universe and ultimately reach a singularity, while the black hole, if isolated, can later evaporate into thermal Hawking radiation that depends only on its mass spin and charge. On the other side stands quantum theory, in which the evolution of an isolated system is expected to preserve information at a fundamental level. If the final radiation is exactly thermal and uncorrelated with the detailed state of the matter that formed and fed the black hole, that information seems to disappear. Many proposed resolutions attempt to preserve both the success of general relativity in describing the exterior geometry and the basic principles of quantum mechanics. One family of ideas suggests that information is not lost, but encoded in subtle correlations within the Hawking radiation correlations that are not apparent in the earliest simplified calculations, but emerge in a more complete treatment. In this view, the radiation is not perfectly thermal, and the pattern of emitted quanta carries a complex imprint of the initial state, even though any practical attempt to decode that imprint would be hopelessly difficult. Another approach proposes that the effective description of space-time breaks down near the horizon in such a way that the interior picture must be modified. The firewall proposal is an example of this. To maintain certain quantum correlations, it suggests that the region just inside or at the horizon is not smooth for an infalling observer, but instead filled with high-energy excitations that would rapidly destroy any matter crossing the boundary. This scenario departs sharply from the classical expectation that the horizon is locally unremarkable for freely falling objects, and it has sparked debate because it forces a choice between different cherished principles: the equivalence principle of general relativity, the unitarity of quantum mechanics, and the absence of exotic observable effects outside the horizon. A different perspective, sometimes called black hole complementarity, attempts to reconcile these tensions by assigning different mutually consistent descriptions to observers outside and inside the horizon, with no single global account valid for all viewpoints at once. In such frameworks, no observer sees a violation of known principles, but the full description resists being expressed in a single classical space-time picture. Quantum gravity models inspired by string theory introduce another set of tools. In certain highly symmetric settings, it is possible to map a gravitational system with a black hole to a lower dimensional quantum field theory without gravity defined on a boundary. This duality allows calculations of black hole entropy and dynamics to be rephrased in terms of a theory where unitarity is manifest. In these examples, information is not lost, and the evolution of the system is consistent with quantum principles, although these specific models differ from the universe. As observed, they suggest that a complete theory of quantum gravity might allow black holes to be described in a way that preserves information without requiring singularities or classical loss. They also reinforce the idea that the fundamental degrees of freedom encoding the interior may be associated with the horizon area supporting a holographic interpretation. Alongside these theoretical constructions, more speculative possibilities involve changing the global structure of space-time. Some solutions to the equations of general relativity admit objects known as wormholes, which link two distant regions or even two separate universes. In idealized cases, the interior of a black hole can be connected through such a bridge to another space-time with the singularity avoided or replaced by a tunnel. In most of these solutions, the structures are unstable or require forms of matter that violate energy conditions normally assumed to hold. Quantum effects might alter these constraints, perhaps permitting short-lived or microscopic wormholes. If any such connection existed in real astrophysical black holes, matter and information falling in could in principle emerge elsewhere, though no observational evidence for such processes currently exists. More modest suggestions propose that the classical singularity is replaced by a high-density region in which space-time undergoes a transition, potentially leading to a bounce or to the seeding of a new expanding region that remains causally disconnected from the original exterior. In this picture, a black hole interior could be linked to the birth of a new domain with its own effective laws and history, while the original universe sees only an evaporating black hole. These ideas loosely connect black hole physics with models of cosmic origins, but they are highly conjectural and depend on features of quantum gravity that are not yet established. Because direct access to the interior is impossible, progress on these questions relies on consistency checks and indirect signatures. Any proposed modification of the horizon or the interior must reproduce the successes of general relativity in describing orbits lensing and gravitational waves outside, and must align with the observed properties of accretion flows and black hole shadows. It must also respect the thermodynamic relations that link horizon area, surface gravity, temperature, and entropy, or explain in a controlled way how those relations are altered. New observational capabilities may provide additional constraints. More sensitive gravitational wave detectors could search for small echoes in the post-merger signal that might arise if the horizon is replaced by a partially reflective surface or by near-horizon structure. Higher resolution imaging of supermassive black holes could reveal tiny departures from the expected shadow shape. Precision timing of flares near the innermost stable orbits might uncover anomalies in the orbital frequencies. So far, within current uncertainties, observations remain consistent with standard black hole models, but the growing precision of measurements continues to shrink the allowed space for alternative scenarios. Even if no deviations are ultimately found, the process of testing these predictions refines understanding of how black holes interact with matter and light in the strong field regime. Through all of this, the central theme remains that black holes sit at the intersection of gravity, quantum theory, thermodynamics, and cosmology. They are formed from ordinary matter through well-understood astrophysical processes, yet they exhibit properties that seem to require a new layer of description. Their horizons behave like thermodynamic objects with temperature and entropy. Their interiors push current theories to singularities, and their evaporation raises questions about information that touch the foundations of quantum mechanics. Observations reveal their mass spin and influence on surrounding gas and stars, but leave their cores unobserved. Theoretical models offer ways to reconcile these pieces, but no single picture has yet achieved universal acceptance. In the quiet, persistent pull of a black hole, in the bright disks and jets that sometimes surround it, and in the faint gravitational waves that mark its mergers, there is a single recurring pattern. Familiar physical laws operating in an unfamiliar regime, hinting that those laws may themselves be part of a larger structure still to be uncovered. As instruments improve and theories are refined, black holes remain both laboratories and enigmas, guiding inquiry toward a deeper account of space-time matter and information without yet revealing how that account will finally be written.